Okay, well, from previous lectures for Poiseuille flow, the relationship between, Poiseuille, relationship between pressure drop and mass flow rate in a round tube. And for that matter, in any slender enough tube, regardless of cross section, that relationship is delta P equals a constant, and then mass flow rate, length of tube divided by, if the tube is round, the diameter to power 4. For the round tube, this constant, we had it on the blackboard last time, is 128 nu over pi. We're not interested in the value of the constant. We're interested in what the constant multiplies. So the pain in the pocket is proportional to the mass flow rate and then to this ratio. So that means that when it comes to the wish of decreasing the overall pressure drop, that wish translates into playing with the configuration such that, in fact, I'm going to write delta P total is the same C, and then there will be two terms. One will be m dot and then L1 over D1 power 4 plus, and then for the second one, half of m dot, and then L2 D2 to power 4. And our wish to decrease the overall pressure drop or to increase access is synonymous with decreasing this group. So to minimize that, easier to see is that I'm factoring this m dot out in front. And what's left is the object of the game. So the objective is to minimize, I called it in the text, the flow resistance in laminar flow, which is what's left in the square brackets, namely L1 over D1 to the 4, and then 1/2 L2 D2 to power 4. You notice here the 4 variables. If you're, I don't know, I was going to say somewhere between novice and a mathematical genius whose name I will mention very soon, but definitely not schooled in technique, which is what I taught in the previous lecture, meaning you have no experience, then you would struggle with eliminating some of these variables using these constraints and then taking the derivative of the object of the game, this is a capital R, with respect to each of those variables, and then solving a system of 4 equations. That is, if you're somewhere between novice or a genius. Fortunately for you, in the meantime, not back in the States, in the meantime, in the 1700s in Europe, a couple of individuals figure out how to help people like Adrian. And that particular, let's call it technique, is to try the simplest first, or to exhibit modesty or humility, okay? It consists of splitting the analysis into two parts. In the first part, we assume that, so part one, assume that the lengths are known. The reason, meaning there should be a hint here as to why this is the first step to make. It is that these constraints are of two kinds. One is simpler. It has only the lengths. The other one is more complicated. And the technique consists of splitting the analysis into two parts, so that in each part you invoke one constraint, not both. One. And that is, if you assume that L1 and L2 are known, then the constraint you'll be invoking refers to tube diameters, D1 and D2, not to lengths, you see. All right, so these will be disregarded for the time being, and that makes the so-called object of the game dependent on just two variables, namely D1 and D2. I write this conclusion a little bit differently. I put here the capital Phi from the Greek alphabet, and in here I put the so-called flow resistance, which is L1 over D1 to power 4 plus 1/2 L2 D2 to power 4. And I continue with the right-hand side of the volume constraint. The volume constraint depends on, forget about these pi over 4 in front, the geometric factors that I underlined. And in other words, I put here a constant called lambda. There's a reason for lambda, as opposed to some other label. And here I put the group that's supposed to be fixed, namely D1 squared L1 plus 1 plus 2 D2 squared L2. This is the so-called objective. The second group is the constraint. And I wrote it this way because I'm invoking a theorem which is known as Lagrange's theorem of, or method of undetermined coefficients. I'm going to be explicit on this right-hand side of the board. You're very quiet in the classroom. Are you actually talking among yourselves before or after I show up? You're not gossiping? You're not? One of my idols, hugely famous professor from Hopkins, once sent to me a note and then signed it. Adrian, what I just wrote is nothing but gossip. But gossip can be helpful. That's what he said. So you guys should feel free to gossip. By the way, you're going to Hopkins from here, you told me?
Yeah.
Yeah, there you go. Before you go, I'll tell you the name of this famous professor. It's safe to talk about him now because he died. Yeah. He spoke fluently Latin and Italian, but he was born in some small town in Indiana. And I asked him, his name is Clifford Truesdell. And I asked him, how come you speak these things better than Adrian? And he said, I go to Italy often and I talk to the waiters in restaurants. That's how he learned. Yeah, it works. And so the theorem, this is Lagrange, his method of so-called undetermined coefficients. This lambda is just one of those. So that's one of the so-called undetermined coefficients. It was called lambda after he died because lambda comes from L. Lambda means L in Greek, in honor of him, okay? Lagrange. Joke moment. His name, Joseph Louis Lagrange. 1700. By the way, 1700s is when calculus was cooked up. People talk about Leibniz and Newton as the creators. The ones who really cooked it up were Euler, D'Alembert, and Lagrange in the 1700s, a few decades after the first two names I mentioned. And then died in 1813. And yeah, what was his nationality?
French.
Who said that? Yeah, well, wrong. He was Italian. He became a French citizen very late in life. His name was Giuseppe Luigi Lagrange. And he was born and brought up in Torino, or Turin, Italy today, in Piedmont. So, so if you're in some restaurant, no, forget, if you visit the university, Politecnico, the first university for engineers in Italy, and talk about Lagrange being French, be very, very careful. Yeah, any of you has that ballpoint pen called a Bic? You've heard of it? Bic?
Yeah.
It's a French pen, right? Baron Bic was, what was his nationality? It's on the blackboard. Italian, from Torino. Yeah, he emigrated to France. Baron Bic was Italian. Yeah, I think based on these videos, they should give me an Italian passport, these very, very modest people who created a lot of stuff. Okay. Oh, and so Lagrange became famous with his math while at the Academy of Sciences in Berlin, where Euler was the number one mathematician. Euler left for St. Petersburg, where he became famous there for giving birth to science in the Russian Empire. But Euler was Swiss. Anyway, late in life, Lagrange was attracted, enticed to move to the French Academy in Paris. And Napoleon was emperor. Yeah, what nationality was Napoleon? It's on the blackboard. He was an Italian from Corsica. Yeah. So Napoleon was very impressed with Lagrange, and he's the one who basically buried him at the Pantheon. All right. Okay, fine. Napoleon. So the theorem is the following. To find the extremum of a function subject to a constraint is equivalent to finding the extremum of this linear combination of the function and the constraint. See that? So instead of minimizing the front subject to a constant second group, I minimize this phi with respect to the only two variables that are still free to vary, namely d1 and d2. And that means doing this, taking the first derivative of with respect to d1 and the first derivative with respect to d2, and obtaining a system of two equations in which these two unknowns, d1 and d2, appear. The expressions are educational. I write them here. Minus 4L1 over d1 to power fifth, and then plus lambda, and then 2 d1 L1, I already said equals 0. And then the second one is minus 4 L2 twice in the denominator d2 to power fifth, and then lambda 4 d2 L2. This is the system. I promise you child's play. This is why this is a method worth learning. You look here. From this system, the dimensions that were assumed known are dropping out. And you have two equations containing this undetermined coefficient, meaning it's a constant, you don't know what it is. And you pull lambda from both equations. I'll just act as if it came from, and conclude that d1 over d2 to power 6 equals 4, which of course means 2 to power 2. And this delivers the first aspect ratio for greatest excess, namely d1 over d2 equals 2 to power 1/3. Two to power 1/3 is a number not much different than 1. It is 1.26. Too bad I erased my drawing. If you would, when you see the video, you can measure the thickness d1 and divide it by the thickness d2 that was on my chalk drawing, and discover that it was exactly this ratio, you see. See, numbers of order 1 are of order 1, but some of them are slightly bigger than 1 and slightly bigger than some other such numbers. So Turns out to be an important constant to remember because it will appear one more time next. With these results, meaning with the relationship between D1 and D2, you can go back into the object of the game, which is this laminar flow resistance. After you have minimized it once. You minimized it in this operation. And when you make these substitutions, oh, by the way, before you do that, you substitute this result into the volume constraint, which I forgot to write again. The volume constraint was pi over 4, and then d1 squared L1 plus twice pi over 4 d2 squared L2. And then when you substitute this discovery, you discover that the constraint is written, the volume constraint takes this shape. The thing I was trying to write first will be written over here. Oh. You're still quiet, even after I told you that the gossip can be helpful. You don't talk. You better learn to join the world of the normal people. Anyway, this operation, when you rewrite the object of the game by taking into account this ratio, you obtain an expression for this flow resistance in terms of only one of the diameters, not both. And that expression is 2 d2 to power 4, this laminar resistance minimized once equals, and then 2 to minus 1/3 L1 plus L2. In other words, you get an expression that depends on the assumed lengths, but also it depends on this single diameter, D2, and by the way, here is supposed to be D2 squared. And that, so you've got two relationships. So you have the constraint, and the constraint combined with this particular expression. In other words, you eliminate D2, and you obtain finally the flow resistance minimized once with respect to the ratio, with respect to those two diameters. And that expression is 2L1 plus L2. So 2 to minus 1/3 L1 plus L2 to power 3. Yeah, that's right. That makes sense. So the dimensions of this R are length divided by length to power 4. So that's meter to minus third. Here, the dimensions of this group are, for the resistance, meter to minus 3 times volume to power 2 is meter to 6, which corresponds to what I have here. So as you trailblaze through the jungle, you need to look behind you and count your footprints and make sure that they line up correctly. In this case, check the dimensions, and you're fine. So, what's left? We have another problem, which is called part 2, which is to minimize the upstairs, subject to the area constraint, which was written originally as A equals L1 to L2. But you have technique. You're not born yesterday. This looks complicated. You want to minimize it. To minimize this expression is the same. So I'm now constructing another Lagrange formulation. To minimize this thing to power 3 is the same as minimizing what's inside the brackets. Think about that. If you want to decrease the inside, this group from 27 to 8, which means 3 to the power 2 versus, 3 to the power 3 versus 2 to the power 3, you might as well decrease 3 to 2, what's inside. Never mind. So the object is the same as decreasing 2 to 1/3 L1 plus L2. And then here's the Lagrange multiplier. And then the constraint is this product, L1, L2, because the factor 2 got multiplied in this unknown leading factor. Okay? And now the next move, and actually the final move, is to find the extremum of this function. Gives you a system of two equations. From those two equations, you eliminate lambda. And the result that sediments at the bottom is the ratio, the aspect ratio L1 over L2, which turns out to be the same ratio as shown here. One thing you learn from this course is not to believe too religiously these results. The message is that the configuration, which means the two aspect ratios, can be anticipated. If the analysis is simple, if the model is simple, then it can be anticipated in the form of some simple expressions. More realistic configurations, more realistic models. Let's say mathematicians with bigger muscles will come up, and they have come up with slightly different results. But the point is that the configuration can be anticipated, meaning you can prove that a drawing with particular aspect ratios is to be expected if you are in the pursuit of easier and easier access. That is the lesson. That is the secret that should, after this course, should be in the back of your mind as you make choices in life or choices in your own design activity. Everywhere, as I said the other day with Aristotle, the object of easy life is to avoid the extremes, which means to avoid bumping into that wall and then ricocheting into the other wall, is to know beforehand the path or the thread of the water. All right, now putting everything together, meaning substituting everything in the expression that was called the objective here. So I'm jumping a few steps. The formulas to remember are the following. If you work back in the formulas that started today's mathematics, you find, based on these two, that the length L1 should be 2 to minus 1/3 square root of the external size. L2 will be 2 to minus 2/3 square root of the external size. So that's one conclusion. And then the resistance for laminar flow, meaning this one that was minimized once, and based on this second result, this resistance has been minimized for the second time. This turns out to be pi squared a to power 3/2 divided by 4 times flow volume to power 2. This is the important result to which we will return next Monday. I'm not finished my lecture. Does it make sense? After all this muscle flexing, this is the champion. The flow resistance depends on size in two ways. The larger the territory to be bathed by this flow, the greater the resistance. That makes sense. This is why the bigger animal has a bigger pump called a bigger heart. Flow volume. The bigger the flow volume, meaning the wider the spacing and all that, the smaller the resistance. Okay. And I will make a sketch to inspire your minds with laminar flow resistance. Well, we've played with two aspect ratios, D1 over D2 and L1 over L2. In the first part of the lecture, we assumed that these lengths were known. That means that our thinking was just like the domain of the possible early at the start of the lecture was in this plane. And in this plane, we found that the resistance can be minimized by varying the D1 over D2. And the bottom of that curve in the first plane, in the first slice, fell on the so-called design space. The design space is on the base of this three-dimensional drawing. And then in the second part of the lecture, today I brought my colored chalk. In the second part of the lecture, we, having learned from the first part, we operated in a second plane, which is this one. In the second plane, we found that by varying L over L, we found that, okay, let me assume that that particular curve is here, meaning that they intersect exactly where, meaning at the point on the base that's represented by these two ratios of 2 to 1/3. And the formula here, the expression that was brought to the minimum twice is called the flow resistance that is the smallest of the smallest. The first one in white was the smallest. Now, the family of those was minimized again to obtain the smallest of the smallest. Yes, you want to impress somebody. I'm not going to talk about your professors here, maybe your girlfriend, your boyfriend. The smallest of the smallest is called the minimum minimorum. This means the smallest. And the second one is of the smallest. Except that Latin, unlike English, has genders. Yeah, it has genders, not sexes. It has genders. And this is for masculine. And of course, formulas, expressions, also in Latin, are feminine. So the equivalent in feminine speech is minima. I wrote it down actually. Yeah, minima minora. Minora. Yeah, sounds great, doesn't it? We're done? So, if you have a daughter, newborn, and she's tiny, you can call her Minora, you know. Nobody will know what that means, but you'll know.